All right, let's jump right in. You've seen it, I've seen it. We are living in this incredible age of AI, right? I mean, models like GPT-4 can do just about anything. Write poetry, smash bugs in your code, even try to explain quantum physics. They're brilliant. But, and this is a big but, there's a catch, a hidden problem that's secretly holding back their full potential.
And that really brings us to the core question we're tackling here. I mean, can an AI be brilliant, but also be brilliant and fast? See, it's just not enough for an AI to be smart. To be truly useful out there in the real world, it's got to be both. But here's the problem. Right now, we're almost always forced to choose one or the other.
So to really get why this is happening, we can actually borrow an idea from psychology. You might have heard of it: thinking fast and slow. The most powerful AIs we have, they operate in what we can call System 2 mode. This is the deep, methodical, step-by-step thinking that gets you those incredible, brilliant answers. The only problem? It's slow. And then you have System 1. That's the fast, gut reaction, intuitive mode. It's awesome for quick, simple stuff, but throw a complex problem at it? Not so much.
And right there, that's the fundamental problem for AI right now. We want the genius-level power of that slow, methodical System 2 brain, but we desperately need it to run at the lightning speed of System 1. Because, let's be real, relying only on these super powerful but slow thinkers, it's just not practical. Think about it. Every time you ask a really complex question, the model has to spin up this long, complicated chain of thought. And that just burns through a massive amount of computational power. We're talking serious money, serious time. The analogy is perfect. It's like hiring a world-class philosopher just to help you find your keys. Total overkill, right?
So what's the solution then? How do we actually get the best of both worlds? Well, this is where it gets really interesting. A group of researchers from Huawei's Noah's Ark lab are digging into this really fascinating and frankly powerful idea called model merging.
So, what is model merging? At its core, it's pretty simple to grasp. Imagine you have two different experts. One is super fast, has a ton of general knowledge, but isn't a deep thinker. The other is a slow, methodical genius. Model merging basically takes these two and fuses their minds into one. The result? A single, unified expert who is both a genius and unbelievably fast.
So here's the high-level view of how it actually works. It's actually pretty elegant. You start with your quick, zippy System 1 base model. Then you take your powerful, fine-tuned System 2 reasoning model. And then, and this is the magic part, you use some really clever techniques to merge their internal parameters, their guts, so to speak. And what comes out the other side? A single model that gets the speed from one and the serious brainpower from the other.
But of course, the real secret sauce is in how you do the merging. It's not as simple as just throwing them in a blender. So the researchers behind this paper basically set up a contest. They took three main approaches, three different families of merging techniques, and put them head-to-head to see which one really works best.
First up, we have our first contender. It's called task vector-based merging. Now, the easiest way to think about a task vector is to imagine it's the specific skill or chunk of knowledge a model learns for a certain job. So this method, it's all about trying to add or average those skills together.
And you know what? The methods in this category, things like ties merging and task arithmetic, they did surprisingly well. The researchers found they could slash the AI's response length, the time it takes to think, by about 50%. I mean, that's half. And they did it with basically no drop in accuracy. A really, really strong start for our first contender. Okay, next up in the ring, contender number 2, SVD-based merging. Now this one is a lot more intense, mathematically speaking. It dives deep into linear algebra and uses a pretty complex technique called singular value decomposition to try and mash the models together. So, how did it do? Well, it was fine. Just okay. The paper itself calls the performance moderate. It seems like it might have its place in some very specific niche situations, but it definitely wasn't the big game changer they were hoping for. A solid try, but not the winner.
And that brings us to our third and final contender. This one is called activation-based merging. And I'll give you a little spoiler here, this is where things get really interesting. See, instead of just averaging out the skills like the first method, this technique literally looks inside the AI's virtual brain. It's analyzing the patterns of which neurons are firing up, which ones activate when it's trying to solve a problem. The whole goal is to pinpoint the most critical neurons for reasoning and then merge those specifically. It's not a sledgehammer, it's a scalpel, a much more surgical approach.
Okay, so there you have it. Our three contenders are on the field. We've got the simple average, the heavy-duty math approach, and the surgical precision method. The researchers threw a whole bunch of really tough reasoning problems at them to see which one, if any, could deliver that holy grail, top-tier accuracy at top speed.
And here we go. These are the results. Let's look at this chart from the paper. It's pretty straightforward. Up the side, you have accuracy. Higher is better. Across the bottom, you have how much the answer was compressed or shortened, so further to the right is better. The sweet spot, the place you want to be, is that top right corner. High accuracy, high speed. And you can already see some clear frontrunners emerging.
So, the big reveal, which method actually won the competition? Well, it wasn't even close. Across the board, one category was the undisputed champion, activation-based merging. That super precise surgical approach of looking at the individual neuron activations, it paid off, big time. And when I say big time, I mean it. How big was the payoff? The best of these activation-based methods managed to get up to a 55% reduction in response length. Just let that sink in for a second. They made the AI's entire thinking process more than twice as efficient, and they did it without losing any of the quality in its reasoning. That isn't just an improvement, that's a massive leap forward.
And this simple table really drives the point home. Look, the baseline model is sitting at about 54.5% accuracy. The first method, task vector merging, gives it a tiny little boost. But then, look at the activation-based methods, things like aim, ties, and sense merging. They don't just significantly cut down that response length, they actually increase the accuracy. Sense merging hits the top of the chart at 56.4%. So they're not just faster, they're actually smarter too.
So what does this all mean for the future? Well, it suggests we're standing right on the edge of a totally new era for AI. An era where that frustrating choice between being brilliant and being fast might just disappear.
And you don't have to take my word for it. The researchers themselves say it loud and clear in their paper, and I quote, "Activation-based merging is the future, as it demonstrates impressive performance in terms of both reasoning accuracy and response length compression." Can't get much clearer than that.
Okay, but let's be clear, this isn't a magic wand that solves everything, at least not yet. The paper is really upfront about the challenges that are still out there. For one, smaller AI models still really struggle to learn deep reasoning this way. And when you scale up to those truly gigantic models, the whole merging process gets way, way harder. So yeah, there's still a lot of work to be done.
But the path forward is so much clearer now. This research gives us a powerful roadmap for building AI that isn't just smart, but efficiently smart. And it leaves us all with a pretty mind-bending question to think about. What actually happens when every single AI can think with the deep wisdom of a philosopher, but at the unbelievable speed of a supercomputer? That's the future this research is pointing to, and it's getting closer, faster than any of us might think.